This problem uses both the rotational and translational versions of Newton's second law. And here we have a pulley that is massive, so its rotational inertia matters this time instead of the old pulleys on our Atwood machines that were massless. So we have to pay attention to how much it resists rotating. And so I'll start off by pointing out that it's got torque from the string that is going to make it start to rotate, and it will have some rotational acceleration, and that's caused by the force of the tension on, which is always going to act perpendicular to the axis. You know, it's like if you can draw a line from the point where the force is exerted, we would always say the force is exerted right at the edge there, and then it acts perpendicular to the line that connects that force to that center rotation point. So then this angle would be 90 degrees. So let's start with the version of Newton's second law for rotating objects, and that would be that we have some of the torques, or net torque, will cause rotation alpha, and then so it's alpha times rotational inertia equals net torque. And then this net torque is calculated by the radius, or lever arm, we would also call it, times the force times sine theta. So I'm gonna, rewrite that out. And then if you go look up the disk, like a solid disk, its I value is 1/2 mass squared. I'm gonna use a capital M because that's what they're using in their picture. R squared, so that's what I is, and then alpha. Now, I guess clarify that all of this torque and rotation is negative because this is clockwise rotation, so I guess I should maybe clarify that. I mean, the negative signs will go away in a second, but maybe we should be consistent here because this is going to rotate clockwise, and so both alpha and torque are negative. Okay, so then we've got, and I suppose on their variable system, sorry, they're using a capital R. So then if we can simplify this at all, then this is sine theta, sine of 90 degrees is going to be 1, and my force really here is a tension force, so I'm going to just call F, instead of F, use capital T. And then this side I really can't simplify much, 1/2 R squared times negative alpha. Okay, so I have two unknowns. I mean, I do know R and I know mass. I'm not going to plug them in yet. But if I could get an equation for T, let's just divide both sides by negative R, and just have an equation for T right now. So then I'll have 1/2 R, so that'll get rid of one of these R's, times alpha. Okay. And then I know I need more info, so for now, let's leave that aside and then tackle the mass, m, little m. Because I do know something about that. I know how to solve an equation and get an expression for its acceleration downward in terms of the forces on it. So let's talk about that. It would, if you drew its free body diagram, it's got tension up and Fg down. Fg is going to win. And then let's say the positive direction is down here. So it's going to have the net force, sorry, let's stick with me, the second law here first. So we have F net is equal to mass times acceleration, and now I'm talking about linear acceleration. So then if I write that out, I have, since I'm picking down as positive, I would say Fg is the positive one, and then plus negative tension, okay, equals mass times the downward acceleration of that little m. And then I'm going to solve this for t as well. So then if I do that, I'm going to have, let's see here, negative t equals, subtract g from both sides, okay? But then if I multiply this by -1, then I end up to get rid of the negative. This ends up being Fg minus mat. Okay. So now I have two equations for tension. And what connects them, though, is the relationship between translational acceleration and alpha. So these are connected, and they're connected by the relationship that translational acceleration equals the alpha times r. And if I look at that's right, it's built in right there. They're already multiplied in there. So let's rewrite this. This is t equals 1/2 m at. It's already in there. So then we're basically solving simultaneous equations here. So let's come down here, drag this business down here, and set these equal. So then I have, I know, let's open that too much space. Okay, so 1/2, the big mass now, the mass of the disk is what that refers to. AT, supposed to be subscript, equals, and then Fg, that's referring to the weight of the little block. I have to remember that. Okay, so now I'm ready to start plugging things in because I have all these numbers. So, for instance, they told me this big M was the disk. Okay, I only have one unknown now, it's just the AT. This refers to mg of the, but now it's like a little m, and 9.8, and then this is little m again, at. So then like add that to both sides. So I'm gonna have half of 2.5. So this is going to be plus another 1.28 t. So on this side, I'm going to have 2.45 at, and on this side, the weight of the little block in newtons, and then just divide, I can get the acceleration, which I had said down was positive. So this is 4.8 meters per second squared down. So that was one of the things they asked me for. And now I can find the rest of the unknowns. So for instance, I needed to know angular acceleration. So for that, alpha would be just divide by the radius. So I would take 4.8 and divide by, it was in centimeters, so make sure you make it into meters. So when you do that, end up getting around 24.
Jackie Jarrett and George Bartek to the box office, please. Jackie Jarrett and George Bartek to the box office.
We had wanted tension as well. We had got this up above. That relationship, we can just substitute in here.
Hi, Jasmine House, Brianna Ashley, Student Services, Jasmine House, Brianna.
Okay.